All right, so I am doing one of the things that makes me feel a little bit awkward, which is to make this video. Making the video is not awkward, but doing this lab is awkward, where I'm sort of, writing code and talking about it. That part is not awkward because I do this in class somewhat frequently, but the students are there and it just seems a little more natural. Now I'm just talking to my computer about the code that I'm writing, and people are watching it, and I'll make a mistake, forget, misspell something, and students are like, you're making a mistake or something. It's not gonna run. Anyways, that just happens because that's what I do. So sorry if you see that I'm like writing something and the code doesn't look quite right. Just give me a second. Once I run it, if it's not right, we'll see that it's a problem. And I try to run the code every couple of edits I make, just to sort of keep stuff like that from happening. Okay, so here's what we're gonna do. We are solving this differential equation, minus u double prime equals f on 0 to 1 with the Dirichlet condition. So we're assuming that u is equal to 0 at 0 and 1. One thing that I want to point out here is this is not a PDE class or a numerical PDE class or anything like that. This is an iterative methods class where we're solving large systems of equations. But a major use case of this is when the system comes from solving numerical PDEs. So in my opinion, I need to sort of show you where these things come from in real life, so it doesn't just seem like we're doing this for no purpose. In addition to that, I just think it's way more interesting that when you're learning a method of how to do something, you can actually see where it gets applied. And so I'm not going to tell you all of the situations in which we might want to solve Poisson's equation or whatever type of equations that we're going to solve. But I think, my videos, at least I hope, and there's going to be discussion about this in the discussion posts, I hope, we sort of are going to see all of the different specific cases where Poisson's equation or whatever equation we're looking at might arise. And so I think it's interesting. So we have this cell down here. This is going to be our solve function that we use. Right now, we're just sort of black boxing it and sending it off to the linalg.solve to solve it for us. But basically, everything that we're going to do from weeks 3 through weeks 9 are going to be to replace that line of code with our own algorithms. So in other words, we can basically do this entire thing, and then maybe the lab next week is just going to be keep this lab as it is, replace this with different solvers that we're going to learn about, and then see how that changes things. It'll be more complicated than that, but that's just the point. Or that's not going to be the exact lab that we do next week. But the point I'm trying to make is the stuff that we're doing this week is just so we have. Just so we know ways that we can actually apply the methods that we're learning. Otherwise, it gets very dull, and you're sort of missing a lot about the class if you don't understand where these systems are coming from. So down here, the solver, like I said, it's going to be a little bit different than what you're doing in the homework. The user, if they want to use this solve function, is going to pass in the X array of equally spaced points, and where 0 and 1 are in this array, and then f is going to be the f function evaluated at those points. So the reason it's set up like this is just so the code runs. I don't like to give a code script like this that doesn't run. So this is just so that it runs. Down here, this is where we're going to test the solver. So I'm going to kind of jump back and forth between here and here just to sort of illustrate what the code is doing. But now notice what we're doing. We're starting with u of x is equal to sine of 2 pi x as a test function. So therefore, we need to determine the corresponding f. So in other words, if the solution is u of x is equal to sine of 2 pi x, we plug it into the equation, do minus the second derivative of sine of 2 pi x, and that's what our f is going to be. So first, I want to sort of write this u, because I'm going to test it. So I want to write a function for u. So I can say def u of x, and then it's just going to return np.sine of exactly that. Whoops. Now, for a function like this, for a one-line function, there's really a better way that we can write this, and it's something called the lambda calculus, or the lambda functionality of Python. It's going to be exactly like this. So u equals lambda x colon, what this means, this notation right here is exactly analogous to what we just saw. It's just going to, u is a function that takes in the parameter x and returns that. That's all it does. Now f, we're going to do something similar. Again, if you take sine of 2 pi x, plug it into Poisson's equation, that is take the second derivative and multiply it by -1, you're going to get, see, it gives us something wrong here. This is the first derivative, so we're not going to use this. It's going to be 4 times np dot sine of 2 pi x, and then we need to have the, hold on a second, np dot, and then times pi squared. Like this. Okay, here we go. Another way that we could do this, and I think I'm going to change it, it's 2 times np pi squared. Whoops. It's 2 pi squared, right? If we do the derivative of this twice, the 2 pi is going to be 4 pi squared, so that's what this is, and then times sine. And remember, there's a minus sign for Poisson's equation, which is why we have that, which is why there's not a minus sign in the derivative. Okay, so what we need to do then, I'm going to start off by saying n is equal to 10. So I want 10 evenly spaced intervals. So then I'm going to say x is equal to np dot linspace 0, 1, 0, 1, n plus 1. So in other words, what x is going to be is going to contain n plus 1 elements. It's going to start at 0, end at 1, and there's going to be an equal distance between those elements. So if I print x, this is exactly what we're going to get. 0 to 1 going up by steps of 0.1. Okay. And then I'm going to need a function f to pass through here for the solver. So I'm going to say f is equal to f of x. Okay, it's really great how that works. So we're going to print this. Now I just want to plot some things here just to make sure that we're on the right track. So plt dot plot x and then u of x. X and then, lowercase u of x. X and then u of x. The reason I'm doing this is because we're going to plot our solutions eventually. And I want to just make sure that I'm starting off right? Because before the beginning of the video, I said sometimes I can just type the wrong thing and not realize that I typed it. I'm going to make this color red. And so essentially, when we plot this, we should be getting sine of 2 pi x, going from 0 to 1. So it should just be one time through the sine function, one period of the sine function. Okay. And of course, it's jaggedy because n is equal to 10. If I make it 100, it'll be much smoother. Okay, but I'm going to make it go back to 10. Okay. All right, there we go. And I'm going to be testing a lot of stuff down here, so I don't need to plot this each time. That's just to make sure that I have things going kind of correctly. All right, so let's go back up here to the solver, and let's get to work on the solver. So what is the main thing that we need to do? Well, we need to construct this matrix, and then we need to call this solver algorithm to solve the system. So I'm going to start off maybe kind of working backwards. So I'm going to say A is equal to, I'm just going to give me some 0. Well, actually, let me back up. So I'm going to say A is the name of the matrix. And then we're going to say U is equal to NP. Actually, you know what? Sorry. Again, this is one of those times where it's very difficult for me to know how to order things when I'm just talking to the screen. So I'm not going to do that. I'm going to change my approach here. I'm going to build the matrix first, just because I want to show you how it's going to look when we build the matrix. So let's first think about this. What are the dimensions of the matrix? Well, if X has n plus 1 points in it, then, if X has a certain number of points in it, we'll call that n plus 1 in just a second. If X has a certain number of points in it, in this case, it'll have 11 points. If this is my X, then I'm only looking at the interior points. Those are the only unknowns, the interior points, because for this problem, U of 0 and U of 1 are equal to 0. So I'm just looking at the interior points. So if I have 11 points total, it's just the 11 interior points that I need. Okay, and there's 11 unknown. If X has 11 points total, it's just the 9 interior points that I need, and so the matrix is going to be a 9 by 9 matrix. So I'm going to say in is equal to x dot size, plus 1, or sorry, minus 1. Okay, that's the number of intervals. Why am I saying n is equal to x dot size minus 1? Because I want n to be the number of intervals. Okay, and because this is going to be consistent with how I wrote things in class and things like that. Okay, so n is equal to x dot size minus 1. So now what this means is I need to build a matrix of size n minus 1 by n minus 1. So if a matrix has, if the x has n plus 1 elements in it, that means there are n subintervals and n minus 1 unknowns. Now I could do something like this, but this is not what I'm going. I could say a is equal to an n minus 1 by n minus 1 matrix, and then iterate over this matrix and set the entries to either 2 or minus 1 or keep them at 0 depending on the matrix here. But one thing that I kind of want to hammer in is that if there is a common Python operation or a common operation like making a tridiagonal matrix, this comes from solving one of the most ubiquitous equations. And just tridiagonal matrices are something that come up a lot. If it's something like solving or coming up with a tridiagonal matrix, there's probably a NumPy function to do that. And there is, in fact, a NumPy function to do this. And I'm going to do it in a couple of steps just so we can sort of see how it works. So I'm going to start by saying A is equal to np.eye n minus 1. Okay, and what this is going to give me an identity matrix of dimensions n minus 1 by n minus 1, which in this case we need it to be 9 by 9. So this is going to give me, if I multiply this by 2, this is going to give me the diagonal piece of the matrix. And for now, I want to illustrate this. So I'm just going to put that as none for now. And I'm going to print A. So I'm going to come down here. When I run this code, it should print the matrix A, and it should be a 9 by 9, 2 times the identity matrix. So a 9 by 9 matrix with 2s on the diagonals and 0s everywhere else. Oh, I didn't actually call the solver. Well, that makes sense. Oh boy, okay. My solver 1D, and we're doing X and F. See, that was one of those times where if you're watching this, you might have been like, you're making a mistake. Luckily, I found it. Okay. So now what I want to do is I need to subtract a diagonal, or a matrix where the diagonal above the diagonal is 1. And there's a way to do that. So it's going to be minus np.eye n minus 1, k equals 1. Okay, so what's going to happen here, this is going to give me an n minus 1 by n minus 1 matrix, and it says that the diagonal, this part right here, is going to give me an n minus 1 by n minus 1 matrix, and k equals 1 says the diagonal, 1 above the diagonal, is going to be equal to 1. And we're subtracting it, so it'll come out as minus 1. So now if we run this, again, we have the 2s on the diagonal and the minus 1 on the diagonal, 1 above the diagonal. And then similarly, we can do minus np like this. K equals minus 1. That's going to be the diagonal minus 1, or 1 below the diagonal. So I'm going to run it here and run it here, and indeed, that is what we get. Okay, awesome. So we've got our matrix. This right here, A is our matrix. That was sort of one of the main challenges here. Now we need to solve the equation. Now, if I do this, there's going to be a problem here. I'm going to run this, but I want you to think about what the problem. There's 2 problems here. One of the problems is going to make this code not even run. So I'm going to run this here and run this here. Okay, so let's see what this says. This is where the issue is coming from. And this would be the other issue that it's coming from. Okay, I thought I might actually make a wiggle on the code up here. But the issue is this. There's an operand at the core dimension. So size 11 is different from size 9. So what this says over here, this has size 11 by 11, and this has size 9. So, this has size 9 by 9. This has size 9 by 9, and this has size 11. Because remember, what is F? f is simply the function little f evaluated at x. X has n points in it, right? X has 11 points in it. So remember, the issue up here is that I don't need f at I don't need f of 0 and f of 1, so I just need the interior points of this f vector. Well, luckily, there is a great way in Python to do this. So I'm going to show you down here if you don't already know it. So I'm just going to print x. Okay, that's what we have here. Now, this is different from MATLAB. Most programming languages are 0 indexed. MATLAB is not, because it's motivated by matrices. But most programming languages are 0 indexed, meaning that the first element of the array has an index of 0. So when I run this code, it's going to print out this array, and then the line below it is going to print the 0th index of this array, which is 0. Okay, but now oftentimes you want to take a slice of the array. In this case, we just want the numbers going from here to here, and Python has a great way of doing that. So I'm going to do 1 colon, and then I'm going to give the other index. I'm going to do 5 as an example. This is going to give me all of the numbers with index 1. It's going to give me all of the numbers starting with index 1 up to, but not including, the number that has index 5. So this has index 1, index 2, index 3, index 4, and index 5. So it's not going to include 0.5. It's just going to give me 0.1, 0.2, 0.3, 0.4. So I'm going to run this. That's exactly what it gives me. Now, another cool thing is that Python has negative indices. So if I look at x of -1, okay, this is the 0th index. So -1 is going to loop back around and give me 1. So if I do this, it's going to give me a 1. And if I do a -2, it's going to give me, the 0.9. So what I want is I want all of the elements from index 1 up to, but not including, the element with index -1. So I can do this, and this is just going to give me the interior points. Okay, so that's what I have here. Okay, so that shows you how I can come up here. So f, I just want the interior points, so it's going to be 1 to -1. The other problem is that in the equation, I need to multiply it by h squared. Well, what is h? If the x array has a certain number of elements, 1 minus that is going to be the number of subintervals. So if I have 11 elements in my array, like I do for in this particular case, there are going to be 10 subintervals. So h is always going to be 1 minus the length of the h is always going to be 1 minus the length of the x array. So 1 divided by n squared. Okay. And then now we are going to return. So notice we have u like this. We're going to return u. There's going to be another problem with this as well that I want you to think about what the problem is going to be. So I'm going to come down here. I'm going to turn this plotter back on. Okay, so the code ran. Everything is working fine, seemingly. Plot. So now I want to plot these two solutions together. So x like this. Actually, sorry. I need to come up here and say u is equal to that. Okay, so notice u, this function is returning u. So it's just going to, in this statement right here, it's going to return u and put it into that variable right there. Okay. So now what should be happening here is we're going to have a plot. The approximate solution is going to be plotted in blue. The actual solution is plotted in red. And the idea is that they should be close to each other. And as we take more and more ins, they should get closer and closer to each other. But there's going to be a problem when this code runs. But I want you to figure out why this code is not going to run before I do it. Okay, so what's the issue here? It's saying this is the problem. X and Y must have the same first dimension, but have shapes 11 and 9. What this is saying is that X has dimension 11, and U has dimension 9. Or in other words, X has 11 entries, and U has 9 entries. Why is that? Oh, well, remember up here, we solved a 9 by 9 system. And so we're only going to have a 9 by 9. We're only going to have a U with 9 entries in it. But remember, we need to add, this is only the interior points, but we know that u of 0 and u of 1 is equal to 0, so we need to add it by doing this. We'll see another way to do this in just a minute. So what we've done here is we have inserted the number 0 at position 0. So it's just going to say, okay, the index 0, I'm going to put a 0 before that. If I done like 1 here, it would say the index before 1, I'm going to put a 0. And this pinned is going to add a 0 at the end of it. Okay, so now this should be correct. Okay, and notice the blue is the approximate solution, the red is the actual solution. One thing that I like to do down here for the approximate solution is make it dashed, make the lines dashed. That's what that says, because pretty soon they're going to be on top of each other. So notice if I even make something like n is equal to 20, they're going to be almost right on top of each other. And then for something like 100, you know, you can't even tell the difference at that point. Okay, so this is a visual sort of indication that our code is working, at least for this one example. We can do it on other examples as well. Another thing that I want to do up here, I always get this wrong. So remember what I said before, that if it is a common operation in Python, it's probably going, if it is a common sort of vector operation that you might think should come up a lot, there's probably going to be a NumPy thing to do that. So I'm going to do np.pad u and 0. This should do the thing that I want it to do. Sorry, let me go back to 10 here. Here's the reason. I did a 0 there because I wanted it to be padded with zeros. What this number goes here is the width of padding. So what happens is, U is an array that has 9 elements. I want to pad it by a width of 1 with the number 0. Okay, so when I say pad by a width of 1, what I'm saying is just 1 element to the left and 1 element to the right. I want there to be a 0. 1 element to the left of U and 1 element to the right of U. I want there to be a 0. Okay, now this, whoops. Yeah, okay, so this gives the thing. So I'm just to illustrate this, I'm going to print U. I'm going to print U before and after, just so you can see what's happening here. Okay, so this is U before, but notice U after, it had added 1 0 here and 1 0 there. Another thing that I think I can do, if I do a 1 here, it's going to pad it, and the value is going to be a 1 instead of a 0. No, sorry. I should not have done that because I forget exactly what... Sorry. I forget exactly what the syntax is. I'd have to look it up. Anyway, sorry about that. I'm not that sorry because also I'm just kind of experimenting here. Or not experimenting. Show you how I think about things. But I also want to show you that if I change this to a 2, just to get just illustrate what's going to happen, this code is not going to run again. But notice what happens is that it pads it with 2 zeros there and 2 zeros there. This is something that in one dimension is nice to use, but we could have done it pretty easily as well without using this function. In 2 dimensions, this is going to be very incredibly nice to use. Okay, so let me just get back to what we had. Okay, so there we have that. Another thing that we can do here is, you know, we have all of these sort of intermediate variables. One thing that we could do is just put this all down here. Like, we're not doing anything with U other than returning it. So I could have this, and then, I could have the following. np.pad this, and then 1 like this. Okay. And then just get rid of this right here. It's really sort of, in my opinion, it's a matter of taste. I mean, if we wanted to get sort of really crazy, we could just inline all of this stuff right down here. You know, I could take this A here and replace it like that. Oh. Okay, in my opinion, once it sort of runs over this dashed line right there, it means this is a little bit too long. So, again, I guess it's partly a matter of taste here. This would be my preferred way of doing it. On the other hand, the way that I had it, I think in terms of just sort of maybe if it's your first time doing a lot of programming, I think this might be a little clearer to look at just the first time. Anyways, okay. So that is it for this example. Let's move on. Sorry, I'm trying to see. Okay, so let's move on now to a slightly harder example. Yeah, let me just make sure that I've got everything going the way that I need it to go here. So if it's not obvious, I have my own lab that I've already done that I'm sort of using as a guide, so I'm not having to, if there is an issue, I kind of know what I'm doing wrong, or I have a cheat sheet. Okay, now what we're going to do next is we're going to do the finite difference solution to this equation right here. So now this is a little bit different. This was something that I didn't go over in class. I don't think I went over this in class. Now I can't remember. I will let you read through this, but what's going to happen down here? What's going to happen down here is that this is the matrix. Oh, sorry. Okay. This is what the matrix is going to be. These numbers right here, what are these numbers right here? Because they have these half indices. So these half indices are going to be evaluated at the midpoint of the subintervals. So we've got subintervals. Let's say we're going to take 10 subintervals again. We have 10 subintervals. And what's going to happen is that we're going to look at like A1 minus a half. That's A sub 1 half. That's going to be evaluated at the midpoint of the first interval. And A1 plus 1 half, that's 3 halves. That's evaluated at the midpoint of the second interval, so on and so forth. Now, our function here is taking in, again, x values, f values, and then a values. Okay, what are the a values? Well, the a values are going to be, again, evaluated at these midpoints right here. Okay, so if you think about what the shapes of these things should be, x should have, let's say, n plus 1 points in it. F should have n plus 1 points in it. The number of points in A should equal the number of subintervals, which is going to be n if x has n plus 1 points in it. Okay, so just make sure you understand everything that I just said there. Okay, so now I'm going to start as I did above. And we're going to say n is equal to x dot size minus 1. Okay, now that suggestion I gave, I think, was just a little bit crazy. So now we need to construct the matrix. Okay, so now we need to construct the matrix. So what's going on here? Let's maybe look along what the upper diagonal should be first. So let's actually notice something here. 2 minus a half is the same as 1 plus a half. So this matrix is a symmetric matrix. So what are these entries right here going to be? So along the top of that, along the diagonal above the diagonal, we have 1 plus 1 half, and down all the way to n minus 1 minus a half. Okay, so what we have 1 plus 1 half. This is A evaluated at the midpoint of the second interval. This is A evaluated at the midpoint of the second to last interval. Now the matrix A, the array A, okay, the array A has A evaluated at the midpoint of each interval. Okay, so here's what we're going to do. I can't use A for the matrix anymore. I'm going to use M. So N is going to be equal to NP dot diag. And now what this is going to do is it's going to give me a matrix where the specified diagonal is going to be the array that I passed in. So I want A going from 1 to -1. Okay, so why do I want that? Well, again, A tells me the value, the array A here tells me the value of A evaluated in each subinterval. On the diagonal above the diagonal, I'm going to have A evaluated at the second subinterval to the second to last subinterval. So that's what this is going to give me, or the half point of the second interval to the half point of the second to last subinterval. That's what this is going to give me. But I want this on the upper diagonal, so I'm going to say K is equal to 1. And I want minus that, because there's a negative. And then this is going to be minus np dot diag, whoops, A of 1 to -1. Also, there's something else that I want to point out here that I didn't before. There's an np.diags function that will have all of this in one that you can do all of this in one thing. Okay, so there's an np.diags function that you can look up, and you can write this as just A equals np.diags, just one np.diags to get this. Anyways, that's something that I wanted to mention. All right, so where are we here? So this right here is going to give me a matrix with the upper diagonal and the lower diagonal. Okay, and I want to test this. So again, oh, by the way, there is a very irritating problem with Jupyter Notebooks. Notice that this is not giving it, even though in this function I haven't defined what U is. Since I've defined it up here, in this sort of global scope or whatever, U is defined, and it is accessible to this down here. So if I didn't change this, this code would compile just perfectly well, or run perfectly well. It's not compiled; it would run perfectly well, and that would be the U that it's going to return here. Anyways, something to keep in mind, can cause bugs when we're dealing with notebooks. One of the reasons that notebooks are a little challenging to use. Anyways, print m, and so I don't make that mistake, I'm going to say U is equal to none now. So now, because the more local scope, U is equal to none, it doesn't have to go to the more global scope. All right, now down here, I want to figure out how we can figure out how to do this A thing at the half subintervals. And now notice that even though I have X defined above, I want to redefine all of my variables in each cell. In each cell, I only want to use the variables of that cell, unless it's like a function from before, which is what I have here. Okay, so it tells me what I want to test it with. This e to the minus x is my f, and that's my u. So I'm going to define, and a is 1 plus x to the power of -1. So notice that this gives me something close to what I want, except I really need this to be minus that. And this gives me the right thing there, but I don't like to actually write it like that. You can do that if you want. For some reason, I guess I'd like to do that. I don't know which one is better. Maybe somebody can tell me. And then this does something well. This tells me exactly what I want, I think. X times e to the x, and then minus 2e over 3. I'm just going to do np.e. And then that is times x squared plus x. See, this needs to be x squared over 2. So Gemini doesn't always get it right. Like that. Okay. Okay, good. Okay, so what can I do with x? Or what? So again, the new thing here is I need to figure out how to get a evaluated at the half points. There's a couple of ways that we can do this. I'm going to start off by saying n is equal to 10 again. And I'm going to need to know what h is. So h is going to be equal to 1 over n. Whoops. And I'm going to make my x array. So x is going to be equal to np dot linspace 0, 1, n plus 1. Okay. Now what I need to do is I need to get, like, this tells me what x is. It's going to give me, again, if I print x, it's going to give me 0 to 1. Now what do I need for my a vector here? I need to know what a is evaluated at 0.5, 1.5, so on and so forth. So what I need to do is I need to take this array right here and add 1/2 to each element. That's going to give me 0.5, sorry, not add 1/2, add half of h to each element, add half of the step size. Okay, if I did up to 1, then I would get 1.05, which is not what I want. So I'm going to come down here. I'm going to do this in a couple of steps. I'm going to call it x half. I'm going to start by just taking the first index all the way up to the last index. Then I want to print the 2. Okay, exactly what we should expect. But now what I want to do is add 0.5 times the step size. And now what this should be is 0.05, 0.15, so on and so forth. Okay, perfect. This is the thing that I want. And now A is going to be A evaluated at the x halves. Okay, perfect. And now this is what x is. So I'm just going to print A for now so we can see what it is. This is what our A is. And now up here, this is our M. I want to print M, and I'm going to come down here just to see that see if I'm doing everything correctly. My solver 1D XFA. Now what should happen when I run this code, it should print A, and it should also run this solver up here, which is going to print the matrix M. The matrix M should be a 9x9 matrix. The diagonal is 0. The upper diagonal should be the negative of those elements, and the lower diagonal should be the negative of those elements as well, and everything else equal to 0. Again, I'm just doing this just because I want to run the code every few steps, just to show step by step what's going on. I understand if you have a lot of experience programming, that might get a little bit frustrating. If so, just watch this on double speed or something like that. But there's some people in this class who don't have as much experience programming. Anyways, and there's also people like me who make errors like this. Oh, I don't think I ran this code yet. So another irritating thing that I should probably not be doing it this way, but I am, is I have a function up here called mysolver1d, and down here I'm using that name again. So that's the error that just happened there. Okay. Oh, okay, so the problem here is that I need to say k is equal to -1. So what was happening up here is if you don't put k is equal to anything, it defaults to k equals 0. So it's trying to come up with a diagonal matrix where that was on the diagonal. This would be an 8x8 matrix then if k is equal to 0. Okay, so there we go. All right, so this is the matrix, and notice that this entry is exactly what it should be. The problem, though, let me turn it down to n is equal to 5. Okay, so this is our A right here, and notice the diagonal above that diagonal is minus that, and minus that, and minus that, and the same thing for the diagonal below the diagonal. I had to change from 10 to 5 just so everything would fit here. Okay. And now up here, what do we need to do? Well, I need to add the diagonal, the actual diagonal. Notice the diagonal. Okay, what is the diagonal? 1 minus a half is a half. 1 plus a half is 3 halves. So if you think about what we're doing here, then is this like the first entry in the sum is going to be A evaluated at the midpoints of this is the midpoint of the first interval, then the midpoint of the second interval, the third interval, all the way down to the midpoint of the second to last interval. And this is going to be the midpoint of the second interval, the midpoint of the third interval, all the way down to the midpoint of the last interval. Okay, so now what we need to do here then is we're going to have np dot diag. Whoops. Okay, so a 0 to -1 is going to give me the midpoint A evaluated at the midpoint of the first interval up to but not including A evaluated at the last interval, meaning the A evaluated at the midpoint, or sorry, the midpoint of the first interval up to the midpoint of the second to last interval, and then plus A1 onwards. Okay, and this is going to give me, if you just do a colon right here and don't include an integer, it's going to give you the whole array. Okay, so let me illustrate that down here. So this is what A is. So I'm going to remove this print statement here for now. So come down here. This is what A is. If I do 1 to the final thing, okay, so what's going to happen? This is A, and if I do A1 colon, it's going to give me this right here, which is the 1 index up to the second to last index there. Okay, anyways. Okay, so here's what we're going to have coming back up here. All right, this is what we have. Now, I don't like to have the code running over this line right here. So I'm going to say m is equal to m minus that. Or we could say m is equal to m minus equals, and I'm going to have to change this minus sign to a plus. Okay. Okay, so that is my matrix. I have constructed my matrix now. So now I'm just going to say u is equal to this solve command again, or this solve function. M is our matrix. This is the h size, and we're squaring it, multiplying it by just the internal part of our matrix. We're going to pad it like that. Okay. So everything should work well down here. And just said u is u is going to be equal to that. Okay, and just like I did above, I'm going to do plt dot plot x u of x. This is going to be the actual one. Okay, I just want to make sure. Wait, why is this all of a sudden not? Let me see where the error is. Notice the problem here. I have f defined up here, and it's using that f instead of the f down here, which is what I need to have. So f is going to be equal to f of x. Okay. Oh. Okay. There we go. All right. Okay, that's not the solve. That's not the approximate. So plt dot plot x u color equals blue. No reason to have a space there other than I'm putting one. Okay, now that does not look quite like what it needs to look like. Oh, because I did. Well, no, that's right. I think maybe I might have typed something here wrong. Let's see. F is equal to minus e to the x. This is 1 over x. X times e to the x minus don't think this is the issue. The issue, so the red thing here is the more or less correct thing. The issue is this blue thing, and I don't think it's just because of this. Wow, what have I done here? Saying that the matrix is singular. Well, this is just awesome. I'm glad you guys are getting to see this happen. Am I doing something wrong here? Okay. Okay, yeah. Oops. So obviously that was embarrassing, but I'm not sure why that was a problem. M plus equals minus that. All right. I have no idea what happened. Maybe I didn't have the minus equals there before. Sorry about that. There's probably another time where you guys are like, dude, sorry. Okay. There. All right. So now everything works perfectly. Okay. And now let's finally move on. I'm probably going to split this lab into two videos. One where I look at the 1D problem and one where I look at this problem. Okay, so there's not going to be much of a change here. What is a change? Well, we already have our A matrix up there. We're just going to literally copy and paste that code. Now we need to do the B matrix, and now we need to do the C matrix. The good news is that we don't have to worry about the half stuff for the we don't have to worry about the half stuff for the B and C. Okay, so again, we're going to come down here. We can sort of just see how we're going to go through this now. In is going to be equal to x dot size minus 1. So I do want to say one thing in the lab that I sort of have already typed out that I'm going to post. I say in is equal to x dot size minus 2. So things will look slightly differently than what I have here. But I just want to warn you that. So now I'm going to make the three matrices: a matrix for A, a matrix for B, and a matrix for C. So MA is literally, I'm going to come up here and copy and paste this. Except I need to make sure to change it to MA. So that's MA. That's MA. MB is going to be the B matrix. Well, okay, so what is the B matrix? Well, this is B evaluated, the B function, the transport term, evaluated at the interior points. So that's what this is. So it's going to be 0.5 and multiplied by a half. Notice there's a half there. 0.5 times NP dot diag, and then exactly this right here. Nope, thank you. That's, well, so, oh yeah, so the other thing to point out here is notice that B is not symmetric. B is no longer symmetric because we have B1 through down through Bn minus 2 here, or sorry, B1 down through B. We have B1 down through the Bn minus 1 here, and then that's what we have down here. Wow. I'm having a hard time spitting out what I need to. So again, the B array is B evaluated at the points, at the interior points. On the upper diagonal, it goes from B1 down to not the second to last, but the one before the second to last. Man, I'm butchering that. So this is not right. This was the suggestion that Gemini gave me here is not right. So we're gonna have b 1 to minus 2, and this is gonna be k is equal to 1, and then minus np. Sorry, I need to multiply it by 0.5. 0.5 times. Okay, now this. Okay, I'm gonna get rid of this for now. Now this is right. 1 to minus 2. Or no, this isn't right. 2. Notice we're starting to 2 down to n minus 1. Okay, there we go. And k is equal to minus 1. But notice I've got the 0.5 here, the 0.5 on both of them. And also notice that I need to multiply it. Notice that I need to multiply it by h. So h times b. So I need to multiply this by h. H is n. So there we go. Okay, 0.5 over n. Sorry, h is 1 over n. So then we have that. And then for MC, this is going to be the diagonal. Again, we're going to look at the interior points of C. So the interior points, and then we need to multiply it by h squared. Okay, and so we're going to have 1 over n squared, and then times np dot diag, and then we're going to go minus 1, sorry, 1 to minus 1. There we go. All right, whoops, equal to that. And then m is equal to this. And then all of this great stuff it already did for us because it knows what we want to do. So Gemini is learning a little bit. Okay, and that's what we have. And that's what we're going to return. So, okay, now for solving it down here, or for testing it. Okay, so I am going to just, because everything is just exactly what we had before. Well, actually, no. I'm not going to do that. There's two things for testing. Instead of solving this equation explicitly, it says to use a SciPy solver to get a numerical solution and plot the two solutions together. So it tells you what A, B. I tell you what A, B, and C are. I'm gonna copy the code. I'm not gonna write out the code for the SciPy thing. I'm just gonna let you look at what the code should look like. That's what it is, and then I'm gonna let you think about that. And maybe in a later lab, I might give more information on this, but I'm already running low on time here, and I still have one more video to make, so where I do the 2D stuff. Okay, so I just want to plot. So let me load everything. Sorry. So f is going to be equal to lambda. So here's here's going to be something that's a little bit challenging. We want it to be 1. We actually need to do 1 times 0 times x. So here's the reason. If x is not modified here and a numpy array gets passed in here, which is what's going to happen, the 1 does not get properly broadcast. And so all this is going to do is literally to return the number 1, but we need it to return a numpy array where all of the entries are 1. Okay, so in fact, try to run this code if you just do a 1 without that. Let's see if this is going to be right. A is equal to 1 over x. B is equal to x, and we have x squared there. That looks good. I'm going to start off again with n is equal to 5, like I did above. H is equal to 1 over n. Okay, so we need to do all this like x half stuff. X is equal to np dot linspace, like that, and then the half. Man, awesome. Then it does all of this stuff correctly here. Okay, good. And now u is equal to, and again, notice that I'm reusing the term mySolver again. I'm just going to run this to see if everything runs correctly. X is not defined down here. Oh, yep, okay. 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 The other thing that I need to do is for the solver, I need to have the derivative of A. So I need to define what AP is. So then AP is just awesome. So the reason we need to do that is because for the solver down here, we have to put in what the actual functions are, like for the first order differential equation. And remember, it's minus and then the derivative of A times U. So we have a first derivative for A that we're going to have to worry about down here. Okay. All right, so the code ran fine, and now we're just going to plot it. So plt dot plot x u colors equal to blue, and then something like that. Okay, so what's happening here? Solution, it tells us what the solution is, but the way that the SciPy solves this system of equations, you might remember from your differential equations class that you can write a second order differential equation as a system of two first order differential equations. That's exactly how this system, that's exactly how the SciPy solver works. So that's why you have this, definition of the system and stuff. And what it does is it returns in x of 0 right here, solution x of 0. What that's going to be is it's going to tell you the it's going to give you the it returns like two vectors. Okay, x of 0 is a solution, and in this conception, x of 1 is going to be the derivative of the solution. Or in general, if you have a solution, a differential equation and two unknowns, the top is going to give you the solution to the first, and the bottom is going to give you the solution to the second. Anyways, when we run this, we should get exactly what we want. Okay, very good. Notice this is just for n is equal to 5, and it's already, converging nicely there for us. Okay. Obviously, if we have more complicated differential equations, we'd have to take more finer steps there. That is going to be it for the 1D. It took longer than I wanted it to. And I had to go through this part a little bit faster than I wanted to. But again, if you understand why the upper diagonal is what it is and why the lower diagonal is what it is, all of this should make sense at this point. So that's it. If you have questions about anything I've done, obviously, please ask them on the discussions. I'm going to spend a few hours today working on the lecture videos for next week. And then at the end of the day, I'm going to come back and do the two-dimensional version for Poisson's equation.